So, oh, too loud. Okay, so welcome to the Institute of Theoretical Physics and ICTP South American Institute for Fundamental Research. I'm Roberto Kraenkel. I'm one of the organizers and lecturers. This is Renato Coutinho, which is also organizer and lecturer. We have a third person that comes only in the middle of the week, Marcelo Gomez. So there are some practical things that I want to explain you how this mini course is organized. Okay? So you have, in the morning you will have lectures, 2 lectures every morning. And these are three different mini courses. So I teach fundamentals of mathematical modeling and applied to epidemiology. And how to continue. Essentially teaches the same thing, but with numerical methods, with computers. Okay? I use only Blackboard. Essentially, he uses computers. And then the third course is by Marcelo Gomez, which will be about data and public health data, based on Brazilian data, but widely applicable to other cases also. Okay? So that's for the mornings. And what happens in the afternoon is that you will be divided into 5 groups. Each group will have a project. Okay? And you will have all the afternoons, and including Saturday, to prepare your project, to develop your project, and present results next Sunday morning. Okay? So, and we will talk more about the projects tomorrow, because today is an exceptional day, because we have lectures also in the afternoon. Because the idea is that you have all the at least the basic things on day 1, and then you have enough to start to work. Okay? And so that's it. And the point about the projects is that they are not just projects like do this, step-by-step projects. They are open-ended. So you got an idea, you got a situation involving some epidemic. We have we have malaria, we have bubonic plague, and several things, several diseases. And then the idea is that you will try to not only answer questions, but pose questions about these things. So what is what is the interesting thing to do with this situation? What can we use mathematical modeling to answer questions that have meaning from the epidemiology point of view? Okay? So this will be the thing. Okay? So it's not a project that has already defined which steps you have to take. You will have presented with a situation, then there will be several questions from which you can start to think about it. Okay? We have 2 late afternoon sessions. One is tomorrow at 6. So the idea is then tomorrow we'll get in touch with your projects, and the idea is that you will be reading the material, the references, and so on, and you will be discussing during the afternoon, and then at 6 you have 5 minutes presentation. You have 5 minutes to tell to everybody what is the project. I mean, you don't have to say we will do this and this and this. You will have to say the project is about malaria in a situation is this and that. Are there data or no data, or what is the thing? And what you have, your first thoughts about this thing, okay? So that's the session tomorrow at 6. And then on Thursday, you have questions and answers, Q&A, okay? So you can ask whatever you want, anything. And there will be a way of asking questions also by written questions, okay? So you don't have to raise your hands and speak in public. You can just write down without signing anything. You can make questions, and that's it, okay? And so that's the structure of the course. We will start every day at 9. I ask you to be here at 9. Today we had to start a little bit later because there were still waiting people. But let's try to start at 9 every day. So, yeah. Okay. Any questions about these practical things of the course? So let's start. And the first lecture, I would call it a gentle introduction to epidemics. Okay. So very basic things. We will have some equations, but let's start without equations. So the first thing is the general scope. Which is maybe you think that epidemiology is always about infectious diseases, and it's not. It can be chronic diseases. There are many things in epidemiology that are not infectious disease epidemiology, but we will work with infectious diseases. So that's what you could say, like diseases that can be transmitted, right, in some way. Okay? There are various, when I say transmitted, that can be from person to person, that can be direct, that can be vector-borne. Vector-borne is a jargon in epidemiology, saying that you have the transmission through some intermediate host, which is maybe mosquitoes or ticks or whatever. Okay? So this is also a way of transmission. And then you can have also environmental transmission. You can have, you can get a person that is infected may somehow infect or contaminate water or the air and so on, and then another person that has no direct contact with the first person can get infected through an environmental transition. So there are several ways of transmitting, and we will touch upon them during the course. Okay? So, but now let us make a small brainstorm. Okay? So we will have several kinds of diseases. So one thing is viral diseases, okay? So the etiological agent, the agent that makes you sick, can be a virus. Now let us see what are your, let us make a brainstorm with saying, give me examples of viral diseases. Examples. Hey, come on, it's up to you. COVID? Influenza? Okay, so let's write COVID-19. Influenza is, yeah. Everybody knows what's influenza. Influenza, it's in Portuguese, it's gripe. In HIV. HIV? What? Mpox? Yes. What? Herpes. 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 Herpes zoster, you mean? Maybe. Rabies. Rabies. Mpox. Everybody know what we are talking about. What's Mpox? Everybody knows what's Mpox? Okay. Who doesn't? We can explain. Okay. So, more. Measles? Yes. Hantavirus. Ebola. Hmm? Yeah. Syncytial respiratory. Okay. Yeah, we have a second part here. Okay. Yeah, all horrors of the more. Let's see. There are some of them that are very common. There are some of them that are not so common. But there are many more. Come on, what is viral diseases? Dengue, Zika, chikungunya. Malaria is not viral. Chickenpox, yes. Chickenpox. I didn't hear. Human papillovirus, yes. More. Yellow fever, yes. It's yeah, yellow fever. Which is this? Okay. Okay, but let's stay with humans. Okay. There's hepatitis can be viral, not necessarily, but can. MERS, which is Middle East respiratory syndrome. Similar to COVID, but higher mortality. So lots of diseases, yes. But we are forgetting some of them because they disappeared. So smallpox, is has been one of the most important diseases of humanity. Okay? Everybody knows what's the smallpox? Okay? So that is also the only disease that had been eradicated. There's a difference between eradicating a disease and eliminating a disease. Eliminating is locally. You can say we have eliminated certain disease here. It doesn't mean that it's eradicated. Eradicated is there isn't any case anywhere, and it's not in the environmental, it's not in animals, it's gone. Right? So that is smallpox. But then there are also many of the childhood diseases that we are forgetting because we are vaccinated. You don't have them anymore. So you have rubella and mumps. Let me go here. Mumps. Portuguese is cachumba, and then in Spanish, mumps. Yeah, yes, yeah. Right. And mumps is important. It's cachumba in Spanish. I think it's papera or something like that. Papera. And rubella. All of them are viral diseases. Okay? Let me see if my list has anything important still. Oh, yes. There's a very important one that we completely forgot. It's this polio. Polio is very important. From these diseases, polio has been considered one of the diseases that could eventually be eliminated. But until now, I have failed with that. Although we have a very good vaccine, which really protects you, gives you lifelong protection, like the measles vaccine. Actually, usually we have now measles, mumps, rubella, which give you lifelong protection. And I think I forgot something which is important, which is pertussis. Pertussis is also important, okay, from the viral pertussis. Pertussis, I know in Portuguese, it's coqueluche. I don't know in Spanish. Okay. So, which is also preventable, but it's still not eliminated. So, but that's not the whole story. There's a whole world of bacterial diseases. So, examples of bacterial diseases. What is? Plague, yes. So, bubonic plague. Bubonic plague, yes. Leptospirosis is, yeah, it is. It is. I'm not sure. Isn't that okay? So, malaria is not bacterial. There can be bacterial meningitis. Yeah, okay, that's a double player here. E. coli, yeah, I can. Yeah. E. coli. Tuberculosis, yes. TB. This one is the real important one that has killed legions of people, okay? And one of the great achievements of, say, humanity is to not eliminate, but drive it to a very low level. It's still a threat, but nobody wants to get tuberculosis, but has been managed, let's say, okay? And all of these things here are preventable, and if not preventable, they can be cured by what? By antibiotics. Okay? So antibiotics is the list here is smaller than here, and many of them are now treatable. Okay. So what else? Anthrax, yes, anthrax. Anthrax, syphilis, brucellosis. What? Tetanus? Cholera, yes, cholera. Somebody does. Hmm? Leprosy, yeah. Which has a new name. Okay, let's put this, because there are still other things coming in. So, what's the right name of leprosy? Hansen disease. Okay. Then you have gonorrhea. Also. Well, and you can have also pneumonia. You can get from bacteria. Okay, so, but as you can see, not everything is here. So there are things that are neither viral nor bacterial, but are still infectious diseases. So, example is diseases transmitted by protozoa. Okay? And so you have protozoa, which is a much more complex etiological agent. There are not so many. Can you give me examples of this? Leishmaniasis. Chagas disease. Finally, malaria. Anything else? So, you see there are not many. I have on my list something which it's very, very high mortality disease. It's the African sleeping disease. So, but then you have still some diseases which are due to macroparasites, which we will not study here, because it's still need a different approach from the one that we will be working here. You have to model also the population of the macroparasites, while we will not model viral load, for instance. Okay? So, and this is the most important as intestinal worms. Then, has anybody another? That's difficult, yeah. But there's one which is historically important and which is almost eradicated, which is the Guinea worm disease. Which has another name because it is dracunculiasis, okay? Which is a worm. Typically, that's the worm that goes out of you in the lower part of your leg. And this has been very, very important historically. And you usually, how you get this worm, it's contaminated water. Yeah? And historically, you know this typical sign of medicine, they have the kind of worm and some apparatus to get the worm out. So this is due to, it's the typical medical, say, logo. And that's connected to Guinea worm. And then there are other worms also, filariasis and so on. Okay, so that's the whole world of diseases, and you can imagine that we will not have something as a general model that will apply to all these diseases, yes? Okay, so why I'm talking so much about these diseases, it's one of the things of the school is pay attention to the biological side of your projects. We have people from biology here, from general biological science, and mathematics and physics. So we have majority of mathematicians and physicists, and the point is not just to play with equations. Play with equations is very easy, okay? That's technically, and what is more important is that you have some realism. So the thing about your model is not the difficulties to solve the model or analyze the model, but to know what model is the good one for the situation that you are analyzing. Okay, so that's important. So, it seems evident, but there are lots of papers which are like, I know how to do, say, networks, and I will apply it for anything in the relevant or irrelevant, if it's publishable. Okay? And you know, everything is publishable today, regardless of it's relevant or correct. So let us now look at some epidemic curves. So first thing, I will consider two cases where there are data, well studied. So we will look at plague in London, 1666. You know, this is a very important year for physicists usually. You know why? Almost. It's about Newton, and Newton had told the people that he has discovered what will be the Newton's law and the universal gravitation laws and calculus. So it's, but it was published later. I mean, that's the publication process at that time took some like 10 years. Okay, so and which will obviously this is the origin of the Principia of Newton, but at this year there was big plague epidemic in London. So if you have the means, what would you do? Go to the countryside, sit under a tree and have an apple falling on you. That's why was Newton sitting on, and that's a little bit fantasy, but why is the story about sitting under a tree? Because why was he sitting on a tree? Because countryside, because there was plague in London, and he was rich enough to get the place. So, plague in London, and we will also look at measles. In New York City, and 1962-63. So let us look at some data. Incredibly, we have data from the plague in London because we have data from what? We have data from the number of weekly deaths. Okay, so you can imagine at that time there was not a real surveillance system that could get your data and so on, but there were bills of people that were dead, and then there's the cause, and so you have this. So let us look at this plot. Oh, okay, here is it. So here have the two plots here. So this first one, is this working here? The first one here to your left is the weekly death in London. And you see, it's not very good at time in years now. I mean, 1666 is the year, but this is about, I think it's months on the X. And so what you see is a peak, yes? So, and when you go to measles, you also see a peak. Okay? So let's say, wow, maybe they are similar. Okay? And maybe the models that can be applied to one of them can be applied to the other one. That seems reasonable at first sight. You look at that, say, but there are some particularities. So first of all, the peak for Great Plague is shorter. Okay? And the peak of measles goes up very fast, but decays slower. So first important thing about this is not symmetrical around the peak. It's not symmetrical. Okay? One of the great mistakes that have been made in the 80s was a paper about the newly discovered HIV/AIDS, where one prominent person fitted just a normal curve, a Gaussian around. Say, this will be a Gaussian. So I have the beginning of the Gaussian, I will fit, and so on. So I will know how many people can be infected. So is it important or not? And it was like I think, I don't know, tens of thousands, or maybe 100,000 people that could be infected, which is completely wrong. Millions, yeah? Completely wrong. And this was based on, this will be symmetrical. Yeah? Completely wrong. So, these things are not symmetrical, although sometimes they just look at first sight, are more or less symmetrical. But yeah. Then you can also see that here in the plague, you have some ripples at the end. Okay? So this probably has to do with some stochastic effects. So maybe for this part, you would have to have different models than the ones that we will discuss. And measles starts to go up again at the very end of the season here. And this one, no, this kind of goes to 0 cases. Right? So on the time scale of 1 year, they are still similar, but now you can think that maybe the models can be also very similar with some adaptations for the specific biological facts that distinguish one from the other. But what happens if now I look on a longer time scale? So again, the same thing. In the longer time scale, you have completely different dynamics. Okay? So this one here is about the plague in London. And you have two big peaks. One is in the 20s, the other one is the older peak that we have seen. Okay? And here you have more or less about 70 years. And most of the time you have some few cases that maybe they are imported, or this is a small outbreak that can be dominated. And then you have big epidemics. They are very fast. On this time scales, it's just almost a line. But obviously, it's not a line because we saw it's not a line, okay? But it's very, very fast. On the other hand, measles, it's recurrent. And then you could even look at this and say that should be kind of a frequency, yes? Yeah, is it exactly periodic? But maybe it's periodic in the sense that it repeats itself. It's obviously not a periodic function in the sense that each year you have a different amplitude, different number of people infected. But that's it. That's it. It's very different. So, lesson. Time scales are important. Time scales will determine what kind of model you need. You are looking for a problem that's a sole epidemic peak. You have some kind of model that will work. If you are looking for long-term, say you have long-term data like this ones, okay, 20, 30 years, then on this time scale, you will have different models, or you have to introduce different biological facts that will determine what goes into your models. Okay? So time scales are very important. So can you say first what would be the mechanism that makes this recurrent measles here? What's the mechanism, biological mechanism, that makes you have measles every year, at least until the 60s, because then in the middle of the 60s we have the vaccine, and then you're not almost eliminated. It's not eliminated. But, well, you have seasons, okay, but there's something else. Yeah, they are recurring, but what makes them recur? Recovery. But measles gives you lifelong immunity. If you have measles, you'll never get it again. Well, but the asymptomatic cases are still, people get immune. So the point about immunity is important here, yes? So one thing about measles, which is very important, but we will see this later at our models, is that it's very infectious, very, very infectious. Okay, so on average, a person with measles in a population that is completely without immunity can infect like 18 other persons. Well, that also happens, but usually that was not the story about measles. Measles, there was even the contrary. They put the kids together, so everybody to get measles together. I remember this. I was already alive at the time. And I had measles. It's a childhood disease. So that's an important point. Newborns, that's the point. Measles is, at the modern ages, at the populations that we are talking about, a childhood disease. So every year there are new childs. So even if you get very large proportion of your population has immunity because they had already measles, there are still people that are still replenishing the pool of susceptible people that can have the disease. Okay? That's the thing. Okay? So just for a historical aside here, measles is a childhood disease for many, nowadays essentially for many populations, but that there's nothing particular that it's only that kids can get it. Anybody can get it. And we had, actually we had we had cases here in Brazil, I think 2018 here in the state of São Paulo, we had a lot of cases. And when you look at the age distribution of the cases, obviously there's a peak at people that have less than 1 year old. Why? Because you can only vaccinate kids with 1 year after 12 months. You cannot vaccinate when they are born. So there is this people that are exposed. But then you have a lot of people about 30 years old who had probably not get vaccinated or were born in a time where the vaccine was only 1 dose. Now it's 2 doses. And that was less efficient. Yeah? But then there's another thing. It has nothing to do with kids. We have an historical example where measles infected just everybody, which is the invasion of the essentially Portuguese and Spanish into South America, and the indigenous people didn't have any immunity because they didn't have any measles, and many of them died. And it has nothing to do with being a kid or not. It's just that probably what happened is measles emerged to humanity in the Middle East, and probably coming from some animal. People discuss which would be the animal, actually. And then it's very infectious, and then you have generation after generations, and you go from a disease that covers all population, but at a certain point, you see that you have immunity, and the diseases goes and becomes more concentrated on kids, and over the thousands of years, that becomes, in practice, in these societies, a childhood disease. So, okay, we also, so the conclusion here is timescales are important. But also spatial scales are important. So is there any sense to try to model COVID-19 for Brazil, whole of Brazil? Or is there any sense of trying to model like influenza in countries like Chile? Or hantaviruses for the whole USA? So, these are things that have no sense, because COVID, everybody remembers COVID. You don't have, you have so different spatial scales in a country of the size of Brazil, it makes no sense to apply models that are for populations at a certain place and so on, try to apply this to a country with so many regional differences. So it makes no sense to take, you can obviously draw an epidemic curve for Brazil, and you can write down the equations and so on, but this is not realistic. Realistic, it has to have a time scale, a spatial scale that makes sense. That usually would be for cities, okay? Also maybe for states, okay? And you have to see what are the kind of questions that you are trying to answer with the model. Chile also has regions which are far in the north, and then almost at the Ushuaia region and so on, it's almost at Antarctica. So temperature gradients and climates are very different from one another. And influenza, we know it's influenced by temperature. So there's no sense of making a countrywide model for that. The same thing is hantaviruses. Hantaviruses is a very deadly disease, and it exists in mainly in 2 states, which in USA, which are New Mexico and Arizona, and which are arid places, and where you have some rodents, which are the intermediate host of this disease. Okay, so I know this. When the first cases emerged of hantavirus in the USA, I know of people that had tried to make a model and say, well, let's see what would be the speed of dispersal of these things and so on the scale of the USA. Okay? They got the result that it would have, in 2 or 3 years, gone all over the USA. Obviously, it doesn't happen. That model was bullshit. Right? So, this is important. Space scales, spatial scales are important. And then there's one other scale, which is also important, which we could say it's the populational scale. Okay? What I mean with the populational scale is you have always to ask yourself, what is the population at risk? Okay? So I remember from a paper published years ago about Zika in Colombia, at the very beginning of the Zika epidemics. And they wrote a model. And one thing that goes into the model is the total population. So it took the total population of Colombia, which is bullshit, because it was concentrated on a city. So the populational scale is the population of that city, not of the whole Colombia. Okay? So he tried to calculate reproductive numbers and so on, but all of this based on the fact that the population at risk would be all Colombia, and it was not at that time. Now, it has spread later, but what he was trying to do was concentrated in a city. So the population scale is important, and always ask the question, what is the population at risk? Now, this you have to take into account for your models, which will be a very important thing. So, models. Let's write our first model. So, I think most of you already know what is the modeling scheme of in the basic studies of epidemic dynamics. When I say dynamics, that has a particular meaning. Dynamics means variation of some quantity in time. Okay, so the usual thing is you separate, you divide your population into susceptibles to that particular disease that you are interested. Then they have the infectious persons. And here I mean infectious as a person that is infected, obviously, but is also transmitting. You could separate this in more elaborate models. And then you have the people that get recovered, if you can recover, okay? You cut and get immune, recover and get immune, okay? So this is typically measles, okay? That's because measles gives you lifelong immunity. If you don't have lifelong immunity, then, which we said that your immunity can wane, waning immunity, then you will have something different, okay? And there are also diseases that don't give you any immunity. And the most prominent is gonorrhea. Okay? You can get it one time every. So you draw this diagram, which says that I'm dividing my population in a susceptible class, infectious class, recovered class, and I put some dotted line here saying, going from I to S, saying that the contact between S and I is what promotes a guy from S to I. Okay? So, now we want to know the time variation of the classes of susceptible, infected, and recovered. Okay? Over time, the susceptibles, in this case here, susceptibles, and we will look at this as a closed population. So this is measles on a one peak idea, okay? Not the long time scale. Okay? So then you will say my population can be considered constant at this point. Okay? And because the time scale of the disease dynamics, the peak and the curve, is on some months. And the population changes, the size of population changes over tens of years to have a real change. So you can consider for the epidemic that population is constant. And we will do this. And we also want to take into account that there are people dying and there are people giving birth. So we will consider have a kind of close population. Yeah? So then, if you have this, we want now to run a model with differential equations, which we say that the time variation of the number of susceptibles, which is the derivative, you want the time variation of the number of infected, and the time variation of the number of recovered. So all of these S, I, and R are functions of time, and we want to write an equation which will allow us to determine those functions. So the first thing will be, now, the number of susceptibles in this case can only decrease, yes? Because if nobody is giving birth and the immunity is lifelong, there's no way of replenishing the susceptible class. So it will have a minus sign here, okay? So, and we'll say that because we will need susceptibles and infected. If you have only susceptibles and no infected, if I is 0, then ds dt has to be 0 because there's no way of I'm susceptible to get infected if they are not infected. Okay? So, on the other hand, obviously you also need that there are susceptible. So if S is 0, and this has also to be 0. Okay? So the usual way to write this is to take the multiplication of S times I. You put some constant in front of it, And we will discuss this concept in a moment. And then you put divide by the total population. Okay? So we will discuss why we are dividing this here, and we will discuss what is the meaning of this beta in a moment. Okay? So then all of these guys have to go into this class. So this class receives everybody that left the other class in it, okay? But your disease has a certain typical time scale. How long, for instance, if you are saying measles, it's like a week, even less, 5 days. There are other diseases that are longer and shorter, okay? So these guys will have something here that goes to this here. And this we will model by writing some constant, gamma times R, times I. Okay? So what is this gamma? If you don't have this, this says that I is a function that decays exponentially. Okay? Indeed, you can, using some stochastic methods and so on, you can show that 1 over gamma, that is right here, 1 over gamma is the typical duration of the disease. Not the epidemic, the disease. How long you get sick, right? So better. It's how long you are infectious, right? Because if you have an asymptomatic phase, then you are not sick technically, but you can be infectious. So it's the infectious phase. And then all of these guys get recovered because we are considering a disease that doesn't kill you. And now we have a system of 3 differential equations for 3 variables, and this is nice. So we will study, our first thing is now to study these equations. But as I told you, this is the first class, and this is a gentle introduction, very gentle. So what, before we, is this correct? Yeah. Ah, okay, this is correct, yeah, okay. No, I looked there, and this is not correct, so I got confused. So we have 20 minutes, okay. And so why did I write this term n here? Okay. It's kind of normalized, but let's think about epidemics that we know. Okay? Take some epidemic like COVID, for instance. Take COVID. Okay? You get an epidemic, say here in Sao Paulo. The urban region has kind of 20 million persons. Okay? Then you will have a lot of cases, and if you are on a short time scale, you get a peak and so on. You have a certain duration, and that's it. Now get to a nearby city like Campinas. Campinas has 1 million persons, approximately. Is this epidemic very different from this one? Only at the scale of the total population, yes? But the rest would be the speed of increasing cases and the duration are more or less the same. So you want that your equation be consistent with that the equations actually are only what we call frequency dependent. What is this? So let us define new variables S, I, and R, which are the capital ones, the susceptibles divided by n, the infective divided by n, and the recovered divided by n. Okay, so I'm taking all the S, I, and R, and I'm dividing them by n. Okay? So they are the fractions of susceptibles in the population, the fractions of infectious, and the fraction of recovered in that population. Okay? So now, once you have done this, now you want the equations for the small letters. Okay? That is easy because then you have only to write D, and S will be small s times n. So we will have small s times n, and the n is a constant. It doesn't go into the derivative. I can put it here. Will be equal to minus beta. Then you have s times I will be small s times small I times n squared divided by n. And that's the first equation. Now, this one cancels with this, which gives you ds dt is equal to minus beta s times I, which does not contain n. So the dynamics for the fractions of susceptibles does not depend on the total size. This means that the dynamics here in São Paulo or in Campinas or whatever city, not whatever, it's very small city, doesn't apply, but are essentially the same, except for a scale fraction. Okay, I'm not saying that in a 1 million city you will have exactly the same number of cases as in a 10 million city, but I'm saying that the fraction of susceptibles and the fraction of susceptibles in a small city and in a big city will have the same dynamics. Okay? So the fractions. And then you can do the exercise for all the rest here. Then you will get this equation here. So di dt will be beta si minus gamma I. And dr dt will be gamma r. So no n. Okay? So this is called frequency dependence. Now, why do you think this is so? Why, we can say from a point of view of observation, say, that the dynamics of a disease like COVID or influenza or measles, or many of them, are well described by equations that are only frequency dependent, and therefore you see that n. I mean, I think you said that the n here. If there was no n, there would not be a frequency dependence. Okay, the n would not disappear. Okay? Now, that is what is behind this fact. So brainstorming. Why is it that the dynamics is independent of the total size of the population? Why should this be? What's
because what you are interested about is the rate of encounters between different fractions, not the numbers.
the number of encounters? And we humans, we live into networks of encounters. Your friends, your family, your people that work with you, people that you meet at certain points. It is more or less the same in a small city and a big city. I'm not saying a small city of 1,000 persons. Okay, but this does not depend if you are in Campinas or in São Paulo. You actually have more or less the same number of encounters. Okay, infectious, possibly infectious encounters. There can be some effects for if it's airborne, and then maybe you have public transportation that could give you a kind of effect, but it would be a kind of correction to this basic model. Okay, so it's the structure of the social contacts of humans. And this is not true if you do epidemiology of animal pathogens in many cases. If you have animals, well, they don't have this kind of structure. Usually, I mean, it depends on the animals, okay? But the classic cases is, for instance, is connected to the classic case is connected, for instance, for fishes that are how do I say that are human. I mean, they are in cages. Okay, so the size of the cage is important. Okay, if it's because actually you pack them and their transmissions go through contact of this kind of skin, and so this is not a situation where this applied. You would not have the N here in this case. So it is very interesting that the structure of social contacts depends on kind of contact. For instance, it could be sexual transmitted diseases, and it's the structure of the sexual contacts of the people in the population. But this is usually not so dependent on the size of the population in your city or the population at risk. So very nice. Now, so this is important. You have something here. Okay. Now we can also discuss a little bit more this mysterious beta. Beta, large beta means susceptibles decrease quickly and infection increase rapidly. Okay? So if you have that kind of curve, different betas have different speed of increasing, at least at the beginning. Okay? So it has to do with the infectivity of your pathogen in your society. And that's important. In your society, it's not something that is connected only to the pathogen. It's not a biological. It's a biological plus social effect. And so we could, you could say that beta should be something proportional, okay? So to the infectivity, so that should be something which I will call, for this moment, I will call it alpha, okay? Which is that, for instance, I told measles is very infective. And there are other diseases that are not so defective. For instance, Ebola. Ebola is deadly, and but on average, every person with Ebola can possibly infect 1.5 or 2 persons, and measles it's like 15, 18. So there's some intrinsic thing that is connected to the pathogen. But it's not only that, because beta has to have something which is really biological wired in the pathogen, but it also has to do with the number of contacts that you have. If you have more contacts, then you will decrease more rapidly or increase increase quickly the number of infected, okay? So there should be something also which is, I will call K, which is typical number of contacts. Now, then you would say, come on, there's no such K, because each person has a certain number of contacts, okay? So in what we are seeing here, we will consider that this is the average number of contacts that a typical person at the susceptible group has, okay? And so then there's a lot of things that can be done about this. You could try to model the network of interaction of people, and then you could say, okay, I can take, every person has a certain number of contacts in this, and I just take the average. But this is good for simple networks. For instance, totally connected networks, then most of the time the average is a good approximation that goes into beta. But sometimes you have different networks where you have people that have only a few contacts and have people that have a lot of contacts. A typical example of this are sexual encounters, okay, which is relevant for sexually transmitted diseases. You can look if number of persons, and most of them have over a given period of time, let's say 1 year, they have one partner. But there are a lot of people that have many. Okay, so that is an example of situations where this maybe should have been modified to take into account a kind of dispersion of the number of contacts in the population. Okay? So, but anyhow, it has to do with the number of contacts, the biological thing, the ability of your pathogen, but then you also need something which would be the probability that given an encounter of an infected and a susceptible person, that this actually will give you a new infected person. Right? So, and this probability, obviously, that this has also to do with the alphabet. But it also has to do with what? With the proportion. If I have an infected, he can only infect susceptibles. So the probability of infection given an encounter will depend if the person is susceptible or not, and we can associate a probability that would be S over N. So the probability that the person actually is susceptible, okay? Could be a recovered, for instance, okay? So this thing here would usually go with something like S over N, okay? The probability that the encounter is with a susceptible. And at the beginning of a new epidemic in a population where a whole population is susceptible, then this is 1, okay? So if you introduce a new pathogen, like COVID, COVID didn't exist. And in 2020, it was introduced in the human population and then increased, then everybody was susceptible. So then S would be equal to N. Okay? However, if you have a population that is vaccinated to a certain extent, then this will not be equal to 1. It will be some other number. For instance, the vaccination population of people that have been, the proportion of people that have been vaccinated in this case. Okay? So beta should have all of these things inside. And the point here is this guy is difficult to determine. Because look at your equation. So here, n, you know, it's demographics of your place. Gamma, 1 over gamma, which is a time scale, it's the duration of the disease, which you know. You can even make a better model because disease can take 5 days, 6 days, 7 days, 8 days, or you could make even a distribution, and you can build upon it. But in the first approximation, it's the typical duration, okay, that you know. Okay? Now, this guy here, you don't know. Right? Because how would you know? You'd have to make experiments which are not ethical. To see the probability of one guy infecting the others, okay? So, and even if you did this, that would be not very good, because one thing is people that have participated in an experiment, and other things is people that are living in a place. Okay? So, which means that when you write these equations, and Renato will show you at some point, you will have data, and you want to see if these guys explain your data, then you will have to fit the model. You have to find the values of your parameters that describe this data. And the less, I mean, the smaller number of parameters you have, the more precise is your thing, the better is your model. Because, you know, you have a model with 10 parameters, it can explain anything, which means it doesn't explain nothing. Right? But you know, if you have a parameter with only one parameter, and then it cannot explain any situation, which means that if it actually explains the situation you are studying, it is a good model. So you don't have too many parameters. But you never get to 0 parameters, because this beta is always a parameter that has to be fitted, always. There's no escape of that, because you don't know the value of this guy. Okay? Well, more or less, there can still be a way of inferring beta. And we will see this. This will be connected to the intrinsic reproductive number, which we will discuss in the afternoon. So, you see, we have not done much. We have talked a lot and made only write down the equations. Now, next step in the afternoon is show me the solutions of these equations. Okay, I will show. And then you ask, can they explain the New York missiles effect? Good question, yeah? So maybe yes, maybe not. And then but the very first thing is, I have a totally susceptible population and introduce a very small proportion of infected individuals, say 1. Will there be an epidemic or not? That's the typical question. That's a practical question, okay? And we will find the conditions for having an epidemic if the disease is well described by the SIR model. Okay? Okay, questions about that? Yeah, please. No, because they are not populations. So here, this is a population size. This is a population size, and this is a population size. So I'm just referring the populations with respect to the total populations. Okay. Now gamma has dimensions 1 over time. Why? Here you have population divided by time. Then this one has also to be population divided by time. And this is already population, so gamma has to be 1 over time. which means 1 over gamma is a time duration, and you can show that's the disease duration. So you have no reasons to divide by gamma, by n. The same thing for beta. Okay? They are not populations. They are parameters. More questions? I need one question to end the class, so you better pose one question quickly. You can be in a comment also, instead of a question. Beta, let us analyze. So you need 1 over time is equal to beta, so units of beta, let's say. And here you have, sorry, here you have populations over time on this side. Here you have the beta, then you have populations squared divided by population, which is n, which gives you only p here overhead. So beta, in this case, is also 1 over time. It's rate. But people usually, they prefer to put this in this way. In this way, then they say, okay, this cancels with this, then beta is given by 1 over time times n over times 1 over the fraction of susceptibles. But actually, these are numbers. So they don't have units. Okay, so half an hour coffee break, which is outside upstairs, and then next class with Renato. At 11. Thank you.